For over half a century, rockets have been our only ticket to space. They are loud, dangerous, and incredibly expensive. But what if we could simply ride up? Picture this, stepping into an elevator car here on Earth and emerging in the vast emptiness of space hours later. No explosive fuel, no violent shaking, no risk of catastrophic failure during those terrifying first few minutes of launch. The space elevator is an idea so bold it almost feels like science fiction, yet it is rooted in real physics. It represents perhaps the most ambitious engineering project humanity has ever conceived. A structure so tall it would stretch from our planet's surface all the way beyond the orbit, where satellites hover motionless above the equator. Today, we will explore whether this incredible vision is truly possible and what it would take to build the tallest structure in human history. We will dive deep into the physics that make it theoretically sound, examine the materials that could make it reality, and discover the challenges that stand between us and our highway to the stars. This is not just about building something tall. This is about fundamentally changing how humanity reaches space, making it as routine as taking a trip to another city. So buckle up as we journey through one of the most fascinating concepts in modern engineering, the space elevator. To understand the space elevator, we must journey back to 1895, when a Russian scientist named Konstantin Tsiolkovsky gazed up at the newly completed Eiffel Tower in Paris. Standing 300 meters tall, it was the tallest structure humans had ever built. But Tsiolkovsky's imagination soared far beyond what his eyes could see. He envisioned a tower that would stretch not just hundreds of meters, but hundreds of thousands of kilometers into space itself. Tsiolkovsky called his vision a celestial tower, and while his initial concept was primitive by today's standards, it planted the seed for one of humanity's most audacious dreams. He imagined a structure so tall that at its peak, the effects of Earth's gravity would be negligible, and objects could simply float away into the cosmos. This wasn't just wishful thinking. Tsiolkovsky was already famous for his rocket equation and his visionary ideas about space travel. He understood that humanity needed a better way to reach space than the crude rockets of his era. But there was a fundamental problem with Tsiolkovsky's tower concept. Any material known to humanity would collapse under its own weight long before reaching such incredible heights. The compressive forces at the base would be absolutely enormous. Imagine trying to stack blocks higher and higher. Eventually, the bottom blocks would be crushed by the weight of all the blocks above them. The same principle applies to any tower, and the taller you build, the worse this problem becomes. Let's put this in perspective. The tallest building on Earth today is the Burj Khalifa in Dubai, standing at 828 meters. Even this engineering marvel, built with the strongest steel and concrete available, would collapse if you tried to make it significantly taller. Now imagine trying to build something not 800 meters tall, but 100,000 kilometers tall. The weight would be absolutely crushing, literally. For decades, the space elevator remained in the realm of science fiction. Writers like Arthur C. Clarke popularized the concept in novels like Fountains of Paradise, painting vivid pictures of elevator cars gliding silently up into space. Clarke understood the physics behind the concept, but he also knew it seemed impossible to actually build with the materials available in the 20th century. Then, in the 1950s and 60s, a breakthrough in thinking occurred. Instead of building up from Earth like a traditional tower, what if we built down from space? This revolutionary shift in perspective came from several brilliant minds working independently. Yuri Artsutonov, a Leningrad engineer, published the first detailed technical paper on orbital tethers in 1960. He realized that instead of fighting gravity, you could use the rotation of the Earth itself to keep a structure in space. Around the same time, American oceanographer John Isaacs was exploring similar concepts, and later, Jerome Pearson would refine the mathematics even further. This revolutionary shift in perspective transformed the space elevator from an impossible dream into a theoretically feasible engineering project. The modern space elevator concept works on an entirely different principle than a tower. Instead of relying on compressive strength to hold itself up, it uses tensile strength to hold itself together while being pulled apart. Here's how it works. Imagine a cable anchored to Earth's surface at the equator. This cable extends upward through the atmosphere, past the edge of space, and continues climbing until it reaches geostationary orbit at 35,786 kilometers above Earth. But it doesn't stop there. The cable continues even further out into space, extending to perhaps 100,000 kilometers or more from Earth's center. At the far end of this impossibly long cable sits a counterweight. This could be a captured asteroid, a massive space station, or simply a very heavy structure built specifically for this purpose. The physics of this system are elegant in their simplicity. Below geostationary orbit, gravity is pulling the cable downward toward Earth. But above geostationary orbit, centrifugal force is pulling the cable outward, away from Earth. These two forces balance each other out, creating tension throughout the entire length of the cable. It's like a cosmic game of tug-of-war, with gravity pulling down and centrifugal force pulling up, and the cable stretched tight between them. This tension is what keeps the entire structure stable and upright. The beauty of this system is that instead of fighting gravity, we're using physics to our advantage. The cable isn't being compressed like a traditional tower. Instead, it's being stretched, and materials are generally much stronger in tension than they are in compression. Think about a piece of rope. You can hang an enormous weight from it without the rope breaking, but try to push up on that same rope, and it will buckle immediately. The mathematics of this system are surprisingly straightforward, though the engineering challenges are immense. The cable experiences maximum stress at geostationary orbit, where the gravitational force pulling down exactly balances the centrifugal force pulling up. This is the critical point in the entire structure. If the cable is strong enough to survive the stresses at this point, the rest of the structure will hold together. Once this cable is in place, we can send climbers up and down it. These would be vehicles designed to grip the cable and use it as a track or railway into space. Instead of carrying enormous amounts of fuel like a rocket, these climbers could be powered by electricity. They might use electric motors to pull themselves up the cable, powered by electricity transmitted up the cable itself, or they could be powered by laser beams transmitted from Earth. The climber starts its journey at the base station, probably located on a floating platform in the Pacific Ocean near the equator. The location must be at the equator because that's where Earth's rotation creates the centrifugal force needed to keep the cable taut. Any other location, and the physics simply don't work. The base station would likely be mobile, able to move out of the way of storms or other hazards. As the climber ascends, it passes through Earth's atmosphere in just the first few hundred kilometers of its journey. This is actually one of the easier parts of the trip. Unlike a rocket, which must fight through the atmosphere at tremendous speeds, burning through its fuel reserves, the climber can take its time. It can ascend slowly and steadily, using minimal energy. By the time the climber reaches 100 kilometers altitude, it's officially in space, having crossed the Kármán line that defines the boundary between Earth and space. But it still has tens of thousands of kilometers to go. The journey continues upward, past the orbits of the International Space Station at 400 kilometers, past the Hubble Space Telescope at 550 kilometers, and beyond the Van Allen radiation belts that surround our planet. As the climber approaches geostationary orbit at 35,786 kilometers, something remarkable happens. At this altitude, the climber is moving at exactly the same speed as Earth's rotation. If you were riding in the climber and looked down at Earth, you would see the same continent below you throughout your entire journey. This is the altitude where geostationary satellites orbit, remaining fixed above one spot on Earth's surface. But the climber doesn't have to stop at geostationary orbit. It can continue climbing even higher, out to where the counterweight sits. At these extreme altitudes, the centrifugal force becomes so strong that objects actually want to fly away from Earth. In fact, if you stepped off the elevator at the counterweight, you wouldn't fall back to Earth. Instead, you would be flung outward into deep space at incredible speeds. This creates an incredible opportunity. Spacecraft launching from the upper reaches of the space elevator wouldn't need any fuel at all to reach escape velocity. The rotation of Earth and the physics of the system would simply sling them out toward the Moon, Mars, or the outer solar system. It would be like having a giant cosmic catapult, giving spacecraft a free boost toward their destinations. The energy savings would be enormous. Today, it takes a rocket like the Saturn V, weighing over 3,000 tons when fully fueled, to send just 50 tons to the Moon. Most of that weight is fuel, burned up in the first few minutes of flight. With a space elevator, you could send that same 50-ton payload to the Moon using no fuel at all, just the free energy provided by Earth's rotation. The space elevator would fundamentally change how we think about space travel. Instead of violent rocket launches that consume enormous amounts of fuel and can only carry relatively small payloads, we could have a gentle, efficient transportation system capable of moving massive amounts of cargo and people to space on a regular basis. Imagine space tourism becoming as common and affordable as international air travel. Picture massive space stations being built with materials easily transported up the elevator. Envision solar power satellites being assembled in orbit and beaming clean energy back to Earth. The space elevator wouldn't just be a transportation system, it would be the infrastructure that enables humanity to truly become a spacefaring civilization. The economic implications alone are staggering. Today, it costs roughly $10,000 to put 1 kilogram of payload into low Earth orbit using conventional rockets. With a space elevator, that cost could drop to as low as $100 per kilogram, a reduction of 99%. This would make space-based manufacturing economically viable, enable massive space habitats, and open up the solar system to human exploration and colonization. But of course, the devil is in the details. Building such a structure would require solving some of the most challenging engineering problems humanity has ever faced. We would need materials stronger than anything that currently exists, construction techniques that work in the vacuum of space, and solutions to countless technical hurdles that we haven't even identified yet. Yet the fundamental physics are sound. The mathematics work out perfectly. The space elevator isn't just a science fiction fantasy, it's a real engineering possibility waiting for the right materials and technology to make it reality. And as we'll see in the coming chapters, we might be closer to having those materials than you might think. To understand why the space elevator must be built at the equator, we need to dive deep into the physics of orbital mechanics and Earth's rotation. This isn't just a matter of convenience or engineering preference. It's an absolute requirement dictated by the fundamental laws of physics that govern how objects move in space around our rotating planet. Earth spins on its axis once every 24 hours, completing a full rotation that gives us our day and night cycle. But here's something fascinating. Different parts of Earth's surface are moving at vastly different speeds due to this rotation. If you're standing at the North Pole or South Pole, you're barely moving at all, just slowly spinning in place. But if you're standing at the equator, you're actually racing through space at over 1,600 kilometers per hour. This difference in rotational speed is crucial to understanding how the space elevator works. The entire concept relies on matching the rotation of Earth with the orbital motion of objects in space. And there's only one altitude where this perfect synchronization occurs: geostationary orbit at 35,786 kilometers above Earth's surface. At geostationary orbit, a satellite moves at exactly the same rate as Earth rotates. From the ground, these satellites appear to hang motionless in the sky above a fixed point on Earth's surface. This is why your satellite dish at home points in one direction and never needs to be moved. The satellite it's communicating with is always in exactly the same spot in the sky, day after day, year after year. But geostationary orbit only works above the equator. If you tried to put a satellite in a geostationary orbit above New York or London or any other location away from the equator, it simply wouldn't work. The physics don't allow it. The satellite would drift north and south in a figure-8 pattern, never remaining stationary above any one point. This is where the magic of the space elevator reveals itself. The cable must be anchored at the equator because that's the only place where the physics align properly. Above the equator, geostationary orbit creates a perfect balance point where the inward pull of gravity exactly matches the outward pull of centrifugal force. Let's break down these forces in detail. Gravity is constantly trying to pull everything toward the center of Earth. The farther you get from Earth's center, the weaker gravity becomes, but it never disappears entirely. Even at geostationary orbit, gravity is still pulling with about 3% of the force you feel on Earth's surface. It's weak, but it's still there, still trying to pull the cable downward. On the other side of this cosmic tug-of-war is centrifugal force. As Earth rotates, anything connected to it wants to fly outward, just like when you're on a merry-go-round and feel pushed toward the outside. The faster the rotation and the farther you are from the center, the stronger this outward force becomes. At Earth's surface, gravity is much stronger than centrifugal force. That's why we don't go flying off into space despite Earth's rotation. Gravity keeps us firmly planted on the ground. But as you climb higher and higher, gravity gets weaker while centrifugal force gets stronger. Eventually, at exactly 35,786 kilometers above the equator, these two forces balance perfectly. This balance point is absolutely critical to the space elevator's design. Below this altitude, gravity dominates, and the cable is pulled downward toward Earth. Above this altitude, centrifugal force dominates, and the cable is pulled outward away from Earth. The cable experiences its maximum stress right at geostationary orbit, where these opposing forces create the greatest tension. But the cable can't stop at geostationary orbit. If it did, there would be no net outward force to keep it taut. The cable must extend far beyond geostationary orbit, out to perhaps 100,000 kilometers from Earth's center. This extended portion acts as a counterweight, providing the centrifugal force needed to keep the entire cable under tension. The mathematics of this system are surprisingly elegant. The total mass of cable above geostationary orbit must be greater than the total mass below it. This creates a net outward force that keeps the cable taut and prevents it from falling to Earth. It's like a cosmic balance scale, with the lower portion of the cable on one side and the upper portion plus counterweight on the other. The cable doesn't have to be the same thickness throughout its entire length. In fact, it would be incredibly wasteful to make it uniform. The cable experiences maximum stress at geostationary orbit and minimum stress at its ends. An optimally designed cable would be thickest at geostationary orbit and taper toward both ends, like a long, thin spindle. This tapering is crucial for minimizing the total mass of the cable. If you made the cable thick enough to handle the maximum stress throughout its entire length, it would be enormously heavy and expensive. By tapering it appropriately, you can reduce the total mass by a factor of 10 or more while maintaining the same safety margins. The orbital dynamics also create some interesting effects throughout the length of the cable. Below geostationary orbit, the cable is actually moving slower than orbital velocity for that altitude. This means objects attached to the cable at low altitudes are being held up by the tension in the cable rather than by their own orbital motion. They're essentially hanging from the cable like weights on a string. Above geostationary orbit, the situation is reversed. The cable is moving faster than orbital velocity for that altitude, creating a net outward force. Objects at these altitudes are being pulled outward by centrifugal force, contributing to the tension that keeps the entire system stable. This creates fascinating possibilities for spacecraft operations. A spacecraft could dock with a space elevator at any altitude and instantly have the orbital velocity appropriate for that height. Want to visit the International Space Station at 400 kilometers altitude? Dock with the elevator at 400 kilometers, and you're already moving at the right speed. Want to head to the moon? Climb up to 50,000 kilometers or higher and release. You'll already have more than enough velocity to escape Earth's gravity. The Coriolis effect also plays a role in the space elevator's dynamics. As objects move up and down the cable, they experience forces that try to push them east or west relative to the cable. These forces are relatively small, but must be accounted for in the design of the climbers and the cable itself. Wind patterns in Earth's atmosphere add another layer of complexity. The cable will pass through various wind layers as it ascends through the atmosphere, each trying to push it in different directions. The jet streams at high altitude can have velocities over 200 kilometers per hour. The cable must be designed to withstand these forces while maintaining its position above the equatorial anchor point. Thermal effects also influence the cable's behavior. During the day, the sun heats one side of the cable more than the other, causing it to expand unevenly. At night, the cable cools and contracts. Over the course of a day, these thermal cycles create oscillations that travel up and down the cable, like waves on a guitar string. The cable must be designed to handle these thermal stresses without breaking. The gravitational influence of the moon and sun also affects the space elevator. These bodies create tidal forces that slightly stretch and compress the cable as Earth rotates. While these forces are small compared to the main tension in the cable, they occur constantly and must be considered in the structural design. Lightning is another concern for the lower portion of the cable. As the cable passes through Earth's atmosphere, it could be struck by lightning, especially during tropical storms. The cable would need to be designed to conduct this electrical energy safely to ground without damaging the structure or any climbers that might be ascending or descending. The location of the equatorial anchor point is also critical. It must be positioned to avoid areas of high storm activity, major shipping lanes, and air traffic corridors. Many proposed designs place the anchor on a floating platform in the Pacific Ocean, several hundred kilometers west of Ecuador. This location offers relatively calm seas, minimal storm activity, and plenty of space for operations. The floating platform would need to be massive, perhaps several kilometers across, to provide a stable base for the elevator. It would also need to be mobile, able to move out of the way of severe weather or other hazards. The platform would serve not just as an anchor point, but as a spaceport, with facilities for processing cargo, passengers, and climber vehicles. The precise positioning of this platform is crucial. Even small deviations from the equator would create instabilities in the cable. The platform would need GPS positioning accurate to within a few meters and powerful thrusters to maintain its exact position despite ocean currents, winds, and weather. All of these factors combine to create a complex dynamic system that must be carefully balanced and controlled. The space elevator isn't just a simple cable hanging in space. It's a sophisticated structure that must account for gravitational forces, orbital mechanics, atmospheric effects, thermal expansion, and countless other variables. Yet despite this complexity, the fundamental physics are sound and the mathematics work out beautifully. The space elevator remains one of the most elegant solutions ever proposed for humanity's greatest transportation challenge. If the physics of the space elevator are sound and the engineering concepts are well understood, Then what's stopping us from building one today? The answer lies in one of the most fundamental challenges in materials science: creating a substance strong enough to withstand the enormous forces involved while being light enough to be practical. To understand just how demanding these requirements are, let's talk numbers. The cable for an Earth-based space elevator would need a tensile strength of at least 50 to 60 gigapascals. To put that in perspective, that's roughly 100 times stronger than the highest grade steel used in construction today. But strength alone isn't enough. The material must also be incredibly light, with a density no greater than 1.3 to 1.5 grams per cubic centimeter. This combination of extreme strength and low weight is measured by something called specific strength, which is the tensile strength divided by the density. For a space elevator cable, we need a specific strength of at least 63 million Newton meters per kilogram. That's not just a little bit better than existing materials, it's a quantum leap beyond anything we can currently manufacture. Let's examine why conventional materials simply cannot do the job. Steel, the backbone of modern construction, has a tensile strength of about 400 megapascals and a density of 7.8 grams per cubic centimeter. This gives steel a specific strength of only about 51,000 Newton meters per kilogram. That's more than 1,000 times weaker than what we need for a space elevator. Even if we could somehow make steel strong enough, the cable would be impossibly heavy. A steel cable capable of supporting its own weight to geostationary orbit would need to be thicker at the base than the diameter of Earth itself. Clearly, steel is not the answer. What about more advanced materials? Kevlar, famous for its use in bulletproof vests, is much stronger than steel for its weight. Kevlar has a tensile strength of about 3.6 gigapascals and a density of 1.44 grams per cubic centimeter, giving it a specific strength of roughly 2.5 million Newton meters per kilogram. That's 50 times better than steel, but still 25 times weaker than what we need. Xylon, an even more advanced polymer fiber, pushes the boundaries further. With a tensile strength of 5.8 gigapascals and a density of 1.56 grams per cubic centimeter, Xylon achieves a specific strength of about 3.7 million Newton meters per kilogram. It's better than Kevlar, but still nowhere near sufficient for an Earth-based space elevator. The fundamental problem is that these materials, while impressive, are still limited by the chemical bonds that hold their atoms together. The strength of any material is ultimately determined by how tightly its atoms are bound to each other. Conventional materials, even the most advanced polymers and composites, simply cannot approach the theoretical limits of atomic bonding strength. This is where carbon nanotubes enter the picture. These remarkable structures represent a completely different approach to materials design. Instead of relying on relatively weak bonds between molecules, carbon nanotubes are essentially single giant molecules, with every carbon atom covalently bonded to its neighbors in a perfect hexagonal lattice. A carbon nanotube is exactly what its name suggests: a tube made entirely of carbon atoms arranged in a cylindrical structure. Picture a sheet of graphene, which is carbon atoms arranged in a flat honeycomb pattern, rolled up into a seamless tube. The result is a structure where every carbon atom is bonded to three others, creating an incredibly strong and lightweight material. The theoretical strength of a perfect carbon nanotube is mind-boggling. Laboratory measurements have recorded tensile strengths of over 100 gigapascals, nearly double what we need for a space elevator. With a density of only 1.3 to 1.4 grams per cubic centimeter, carbon nanotubes achieve specific strengths of over 70 million Newton meters per kilogram, finally crossing the threshold needed for space elevator construction. But here's the catch that keeps the space elevator in the realm of future technology rather than present reality. These incredible strength measurements have only been achieved with very short nanotube segments under carefully controlled laboratory conditions. The longest continuous carbon nanotube fibers ever produced are measured in kilometers, not the 100,000 kilometers needed for a space elevator cable. Creating long, continuous nanotube fibers presents enormous technical challenges. Individual nanotubes are typically only a few micrometers to a few millimeters long. To create a useful fiber, billions of these tiny tubes must be aligned and bonded together. Every junction between individual nanotubes represents a potential weak point where the fiber could fail. Current manufacturing techniques for carbon nanotube fibers achieve only a fraction of the theoretical strength. Real-world nanotube fibers today have tensile strengths of about 1 to 10 gigapascals, much better than conventional materials, but still far short of what laboratory tests suggest is possible. The challenge is maintaining the perfect structure and alignment across macroscopic lengths. There are also issues with purity and defects. Real carbon nanotubes contain impurities, missing atoms, and structural defects that significantly reduce their strength. A single missing carbon atom can cut the strength of a nanotube segment in half. Manufacturing processes that can create defect-free nanotubes over long distances remain beyond our current capabilities. Even if we could solve the manufacturing challenges, there are other material properties to consider. The cable must not only be strong, but also stable over time. It will be exposed to ultraviolet radiation from the sun, atomic oxygen in the upper atmosphere, and temperature variations from -100 degrees Celsius in Earth's shadow to +100 degrees Celsius in direct sunlight. Many materials degrade under these conditions. Carbon nanotubes show promise for radiation resistance, but long-term stability remains uncertain. The cable must maintain its strength for decades without significant degradation. Any material that slowly weakens over time could lead to catastrophic failure years after construction. Graphene represents another potential breakthrough material. Like carbon nanotubes, graphene consists of carbon atoms arranged in a perfect hexagonal lattice, but in a flat sheet rather than a tube. Graphene has demonstrated even higher strengths than carbon nanotubes in laboratory tests, with tensile strengths exceeding 130 gigapascals. The challenge with graphene is similar to that of carbon nanotubes, scaling up from laboratory samples to practical materials. Current techniques can produce high-quality graphene sheets only a few centimeters across. Creating continuous graphene fibers hundreds of thousands of kilometers long would require revolutionary advances in manufacturing technology. Researchers are exploring other exotic materials as well. Carbine, a one-dimensional chain of carbon atoms, has theoretical strengths even higher than graphene or carbon nanotubes. However, carbine is extremely unstable and reactive, making it impractical for construction purposes with current technology. Some scientists have proposed using biological materials as inspiration. Spider silk, for example, has an impressive combination of strength and toughness, though not quite at the level needed for space elevators. Researchers are working on genetically engineered bacteria that could produce artificial spider silk or other bio-inspired materials with enhanced properties. The specific strength requirement also depends on the design of the space elevator. A tapered cable, thicker at geostationary orbit and thinner at the ends, can reduce the total mass and lower the strength requirements somewhat. Advanced designs with multiple parallel cables or backup systems could provide redundancy, even if individual cable segments fail. Safety factors add another layer of complexity to material requirements. Any real space elevator would need to handle not just its own weight, but also the weight of climbers, cargo, and dynamic loads from wind, thermal expansion, and orbital perturbations. Engineers typically design structures to be several times stronger than the minimum required, meaning the cable material might need to be 2 to 5 times stronger than the basic theoretical requirement. Manufacturing at the scale required for a space elevator presents unprecedented challenges. The cable would require thousands of tons of perfectly manufactured nanotube fiber. Current production of high-quality carbon nanotube fiber is measured in grams per day, not tons. Scaling up production while maintaining quality would require entirely new industrial processes. Cost is another major consideration. High-quality carbon nanotube fiber currently costs hundreds of thousands of dollars per kilogram. Even with dramatic cost reductions from mass production, the material costs alone for a space elevator cable could reach into the hundreds of billions of dollars. Despite these challenges, progress continues on multiple fronts. Researchers are developing new techniques for growing longer nanotubes, improving alignment in fiber production, and reducing defects in the final product. Each advance brings us closer to the material properties needed for space elevator construction. Some companies are already producing carbon nanotube fibers for commercial applications. While not yet at space elevator grade, these materials are finding uses in aerospace, automotive, and electronics applications. This commercial development is driving improvements in manufacturing techniques and cost reduction. The materials challenge is not insurmountable, but it represents the critical bottleneck for space elevator development. Until we can manufacture materials that meet the demanding requirements of specific strength, length, and stability, the space elevator will remain a tantalizing possibility rather than an engineering reality. However, the rapid pace of advancement in nanotechnology suggests that this breakthrough may be closer than many people realize. Even if we develop the perfect material for a space elevator cable, actually constructing this colossal structure presents engineering challenges unlike anything humanity has ever attempted. We're talking about building something 100,000 kilometers long in the vacuum of space, where traditional construction methods simply don't work. The construction process itself would be one of the most complex operations in human history, requiring unprecedented coordination between Earth-based operations and space-based assembly. The most promising approach for building a space elevator is called the deployment method, and it's as elegant as it is ambitious. Instead of trying to build the entire structure from the ground up, we start from the top down, literally lowering a cable from space to Earth while simultaneously extending it upward to create the counterweight section. The process begins with launching what engineers call a seed cable to geostationary orbit. This initial cable would be relatively small, perhaps only a few millimeters thick, but it would stretch the entire length of the final elevator from Earth to the counterweight position. Think of it as a pilot line, similar to how suspension bridge builders first string a thin cable across the gap before adding the main support cables. Getting this seed cable into position would require a sophisticated space mission. The cable would be wound onto massive spools aboard a spacecraft and launched to geostationary orbit. The spacecraft would serve as the initial counterweight and deployment platform, positioned precisely above the intended anchor point on Earth's equator. Once in position, the deployment begins. The spacecraft starts lowering one end of the cable toward Earth while simultaneously unreeling cable in the opposite direction to maintain balance. This is crucial because the center of mass of the entire system must remain at geostationary orbit throughout the deployment process. If the balance shifts too far in either direction, the cable could either fall to Earth or drift away into space. The downward deployment is a delicate operation that could take weeks or months to complete. The cable must descend through various atmospheric layers, each with different wind patterns and weather conditions. At high altitudes, the cable passes through the jet stream, where winds can exceed 200 kilometers per hour. Lower down, it encounters clouds, storms, and turbulent air that could damage or deflect the cable. To protect the descending cable and guide it to the anchor point, engineers have proposed using a fleet of aircraft and even stratospheric balloons. These would monitor the cable's descent and potentially provide course corrections if wind pushes it off target. The final approach to the anchor platform would be the most critical phase, requiring precise coordination to ensure the cable connects properly. Meanwhile, as the cable descends toward Earth, the spacecraft continues extending cable upward to maintain the system's balance. This upper section eventually becomes the counterweight portion of the elevator, extending tens of thousands of kilometers beyond geostationary orbit. The spacecraft itself might remain as part of the permanent counterweight, or it could detach once the cable is fully deployed. Once the seed cable is in place and properly anchored, the real construction work begins. The seed cable alone would be far too thin to support any significant load. It's essentially a guideline that allows us to build the actual elevator cable. This process, called cable strengthening or cable fattening, involves sending up additional strands of cable material and weaving them together with the original seed cable. This strengthening process would use the first generation of climber vehicles, specially designed construction robots that can grip the seed cable and carry additional cable material up from Earth. These climbers would be much simpler than the passenger or cargo climbers envisioned for the operational elevator. Their only job is to carry cable material and help weave it into the growing structure. The strengthening process starts at the bottom and works upward. Additional cable strands are attached at the anchor platform and carried up by the climbers, which weave them into the existing cable as they ascend. This gradually increases the cable's thickness and load-bearing capacity. As the cable gets stronger, it can support heavier climbers carrying more material, accelerating the construction process. The weaving pattern is critical to the cable's strength. Simply bundling parallel strands together wouldn't provide optimal strength. Instead, the strands must be twisted or braided together in a pattern that distributes loads evenly and prevents individual strands from sliding past each other under tension. This requires sophisticated robotic systems capable of precise manipulation at extreme altitudes. The construction timeline for this strengthening process could span several years. Each trip up the cable adds only a small amount of material, and millions of trips would be needed to build the cable to its full design strength. However, the process is self-accelerating. As the cable gets stronger, it can support larger climbers carrying more material per trip. During construction, the cable must be protected from various hazards. Space debris poses a constant threat. Even tiny pieces of orbital junk could sever the cable if they impact at high velocity. The construction area around geostationary orbit would need to be monitored constantly, with systems in place to track and possibly deflect incoming debris. Weather at the anchor point also affects construction operations. Severe storms could damage equipment or make it unsafe to launch climbers. The anchor platform must be designed to withstand hurricane-force winds and massive waves while maintaining precise positioning. During extreme weather, construction might need to halt entirely. The anchor platform itself represents a major engineering challenge. This structure must provide a stable base for the elevator while floating in the ocean. It needs to be large enough to accommodate the massive forces transmitted by the cable, yet mobile enough to move out of the path of severe storms or other hazards. Current designs envision a platform several kilometers across, essentially a floating city dedicated to space elevator operations. The platform would include facilities for assembling climbers, processing cargo, housing personnel, and maintaining the elevator system. It would also need its own power generation, likely including nuclear reactors to provide the enormous amounts of electricity needed for elevator operations. The platform's positioning system must be incredibly precise. Even small movements away from the optimal position could create dangerous stresses in the cable. The platform would use a combination of GPS navigation, underwater anchors, and dynamic positioning thrusters to maintain its exact location within a few meters of the target position. Cable installation presents unique challenges at different altitudes. In the lower atmosphere, the cable must be protected from lightning strikes and severe weather. Special lightning arresters and weather monitoring systems would be needed. In the upper atmosphere, Atomic oxygen poses a threat to many materials, potentially causing gradual degradation of the cable surface. At orbital altitudes, the cable faces different hazards. Solar radiation can damage some materials over time. The Van Allen radiation belts create zones of intense particle radiation that could affect both the cable and any electronic systems. Thermal cycling, as the cable moves in and out of Earth's shadow, creates expansion and contraction stresses. The cable attachment system at geostationary orbit requires special consideration. This is where the cable experiences maximum stress, and it's also where the primary cable meets any branching structures. Some designs call for a large platform at geostationary orbit that serves as a space station and transfer point for passengers and cargo. Quality control during construction would be absolutely critical. Any weak points in the cable could lead to catastrophic failure. Each section of cable would need to be tested as it's installed, using techniques that don't damage the material. Non-destructive testing methods like ultrasonic inspection or electromagnetic analysis might be used to verify cable integrity. The construction workforce for such a project would be unprecedented. Engineers, technicians, and specialists would need to work in shifts around the clock for years. Some personnel would be based on the anchor platform. Others might work from orbital stations, and ground-based teams would coordinate the entire operation. The logistics of supporting this workforce in remote ocean and space locations would be enormously complex. Backup systems and redundancy are essential for such a critical structure. The cable design might include multiple parallel strands that can carry the full load independently. If one strand fails, the others continue supporting the elevator while repairs are made. The construction process would need to build in this redundancy from the beginning. Emergency procedures must be planned for various failure scenarios during construction. If the cable breaks during deployment, rapid response systems would need to prevent the upper section from drifting away, or the lower section from falling to Earth in an uncontrolled manner. Backup attachment points and emergency stabilization systems would be essential. Testing and commissioning the completed elevator would be a gradual process. The first climbers would carry only light loads to verify the system's operation. Load testing would gradually increase as confidence in the structure grows. Full operational capability might not be achieved until years after the initial cable deployment. Despite these enormous challenges, the step-by-step construction process is technically feasible with advanced materials and robotics. Each phase builds upon the previous one, creating a pathway from current technology to a completed space elevator. The construction itself would drive innovations in space robotics, materials handling, and precision engineering that would benefit many other industries. The construction of a space elevator would be humanity's greatest engineering achievement, requiring international cooperation, unprecedented technical precision, and years of sustained effort. Yet the result would be a permanent gateway to space that could transform our civilization's relationship with the cosmos. The challenge is immense, but so is the potential reward. Building a space elevator means creating a structure that must survive in one of the most hostile environments imaginable. Space is not empty and peaceful. It's filled with radiation, debris, and extreme conditions that constantly threaten anything we place there. A space elevator cable stretching 100,000 kilometers through this gauntlet of hazards faces dangers that could not only damage the structure, but potentially create one of the most catastrophic disasters in human history. Let's start with one of the most immediate and persistent threats: space debris. Earth's orbital environment is cluttered with millions of pieces of junk, ranging from flecks of paint to defunct satellites. NASA tracks over 34,000 objects larger than 10 centimeters, but estimates there are over 130 million objects larger than 1 millimeter. Every single one of these represents a potential projectile that could strike the space elevator cable. The physics of orbital collisions are terrifying. Objects in low Earth orbit move at velocities of roughly 8 kilometers per second. At these speeds, even a piece of debris the size of a marble carries the kinetic energy of a hand grenade. A fragment of space junk smaller than your fingernail could completely sever a space elevator cable, potentially triggering a catastrophic collapse of the entire structure. The debris environment is particularly dense in certain altitude ranges. Low Earth orbit, between 200 and 2,000 kilometers altitude, contains the highest concentration of tracked objects. This includes defunct satellites, spent rocket stages, and fragments from collisions and explosions. The space elevator cable would pass directly through these debris fields twice, once on its way up and once on the way down if it ever fell. But the threat isn't just from large, trackable objects. Micrometeorites, tiny particles of cosmic dust and debris from comets and asteroids, constantly rain down on Earth. Most burn up in the atmosphere, but a space elevator cable would be exposed to this bombardment throughout its entire length above the atmosphere. While individual micrometeorite impacts might not sever the cable, the cumulative damage over years could weaken it significantly. The cable's cross-sectional area makes it a sitting duck for impacts. Unlike a satellite that presents a relatively small target, the space elevator cable would stretch across 100,000 kilometers of space. Even if the cable is only a few centimeters wide, its enormous length makes collision with debris almost inevitable over the operational lifetime of the structure. Some proposed solutions involve active debris tracking and avoidance systems. Powerful radar and optical telescopes would continuously monitor the space around the elevator, tracking every piece of debris that might pose a threat. When a collision is predicted, the entire cable structure might be shifted slightly using thrusters on the counterweight or anchor platform. However, moving something as massive as a space elevator cable requires enormous amounts of energy and time, making this approach challenging for rapidly approaching debris. Another approach involves building multiple parallel cables with significant separation between them. If one cable is severed by debris impact, the others could continue operating while repairs are made. This redundancy comes at enormous cost and complexity, essentially requiring multiple complete space elevators to ensure reliability. Space weather represents another major category of threats. The sun doesn't shine steadily. It experiences cycles of activity that send bursts of radiation and charged particles toward Earth. Solar flares can release the energy equivalent of billions of nuclear weapons, sending streams of high-energy protons racing toward our planet at speeds approaching the speed of light. When these particles encounter the space elevator cable, they can cause several types of damage. High-energy radiation can break chemical bonds in the cable material, gradually weakening its structure. This is particularly concerning for organic materials like carbon nanotubes, where radiation can knock carbon atoms out of their precise lattice arrangement, creating defects that significantly reduce strength. Charged particles can also build up static electricity on the cable, creating potential differences of millions of volts between different sections. This could lead to massive electrical discharges that damage the cable or any climbers attached to it. The cable would need sophisticated electrical grounding systems and surge protection to handle these space weather events. Coronal mass ejections represent an even more severe form of space weather. These are massive eruptions of plasma from the sun's corona that can engulf the entire inner solar system. When a coronal mass ejection hits Earth, it can induce powerful electrical currents in any conducting material, potentially overloading electrical systems and causing structural heating in metallic components. The Van Allen radiation belts pose a persistent radiation threat between about 1,000 and 60,000 kilometers altitude. These are regions where Earth's magnetic field traps high-energy particles, creating zones of intense radiation. The space elevator cable would pass through these belts and be constantly exposed to this radiation environment. long-term exposure could cause gradual degradation of the cable material. Atomic oxygen in the upper atmosphere creates another corrosion threat. At altitudes between 200 and 700 kilometers, atomic oxygen is abundant and highly reactive. This single-atom oxygen readily attacks many materials, causing surface erosion and chemical degradation. The space elevator cable would need special protective coatings or must be made from materials that resist atomic oxygen attack. Temperature variations present ongoing structural stresses. As the Earth rotates, different sections of the cable move in and out of sunlight, experiencing temperature swings from -150 degrees Celsius in shadow to +120 degrees Celsius in direct sunlight. These thermal cycles cause the cable to expand and contract, creating stress waves that propagate up and down its length. The thermal expansion problem is particularly challenging because different sections of the cable experience different temperature changes at different times. As Earth rotates, a wave of heating and cooling travels along the cable's length. This creates complex stress patterns that could lead to fatigue failure over time, similar to how a paperclip breaks when bent back and forth repeatedly. Dynamic oscillations represent another category of structural risk. The space elevator cable is essentially a massive guitar string under enormous tension. Like any string, it can vibrate in various modes, creating oscillations that travel up and down its length. These vibrations can be triggered by wind loads in the atmosphere, thermal expansion, gravitational perturbations from the moon and sun, or movements of climbers on the cable. Some of these oscillations could grow over time through resonance effects. If the frequency of disturbing forces matches one of the cable's natural vibration frequencies, the oscillations could build up to dangerous levels. Engineers would need sophisticated damping systems to control these vibrations and prevent them from reaching destructive amplitudes. The gravitational effects of the moon and sun create tidal forces that continuously stress the cable. As these bodies move in their orbits, they create varying gravitational fields that stretch and compress the cable in complex patterns. While these forces are relatively small compared to the main tension in the cable, they occur continuously and could contribute to fatigue damage over time. Atmospheric effects in the lower altitudes pose additional challenges. The cable must pass through Earth's weather systems, exposing it to lightning strikes, severe storms, and hurricane-force winds. Lightning could carry currents of hundreds of thousands of amperes, potentially vaporizing sections of the cable or damaging climbers. High-altitude winds, particularly the jet streams, create persistent sideways forces on the cable. These winds can reach velocities over 300 kilometers per hour and could deflect the cable significantly from its vertical position. The cable design must account for these wind loads while maintaining structural integrity. Perhaps the most catastrophic risk is complete cable failure. If the space elevator cable breaks at any point, the consequences could be devastating. The section below the breakpoint would fall to Earth, potentially wrapping around the planet multiple times as it descends. The upper section would fly outward into space, possibly threatening other satellites or space installations. Computer simulations of cable break scenarios show terrifying results. If the cable breaks near geostationary orbit, the lower section would fall in a complex spiral pattern, impacting Earth's surface at hypersonic velocities. The cable would burn up partially during atmospheric re-entry, but significant sections could survive to impact the ground with enormous destructive force. The upper section breaking free would carry tremendous kinetic energy as it flies outward from Earth. This could threaten satellites in higher orbits or even pose risks to spacecraft traveling to the Moon or other planets. The debris field from a catastrophic cable failure could contaminate Earth's orbital environment for decades. Emergency systems would be essential to minimize damage from cable failures. These might include explosive charges that can deliberately sever the cable at predetermined weak points, directing the failure in a controlled manner. Quick release mechanisms at the anchor platform could disconnect the cable if sensors detect imminent failure. allowing it to drift away from populated areas. Redundant cable designs offer another approach to managing failure risks. Multiple parallel cables could share the structural load, so the failure of one cable doesn't necessarily doom the entire system. However, this approach requires careful design to prevent the failure of one cable from triggering cascading failures in the others. Monitoring systems would need to continuously assess the cable's structural health. Networks of sensors along the cable's length could detect developing problems before they lead to catastrophic failure. These might include strain gauges to measure stress levels, acoustic sensors to detect crack propagation, and optical systems to inspect the cable surface for damage. Despite these numerous hazards and risks, many of them can be mitigated through careful design and engineering. The space environment is hostile, but it's also predictable in many ways. With proper materials, protective systems, and monitoring technology, a space elevator could potentially operate safely for decades. However, the risks are real and significant, requiring unprecedented attention to safety and reliability in the design process. The challenge is not just building a space elevator that works, but building one that can survive and operate safely in the harsh environment of space for many years. This requires not just advances in materials science, but also new approaches to structural monitoring, risk management, and emergency response systems. The engineering challenge is immense, but so is the potential reward of reliable, safe access to space. Once we have a cable stretching from Earth to space, the next challenge is figuring out how to actually move cargo and passengers along it. Unlike rockets that carry their own fuel, space elevator climbers need a continuous source of power throughout their journey. This presents a unique engineering problem. How do you deliver enormous amounts of energy to a vehicle that's constantly moving along a 100,000-kilometer track through space? The power requirements for space elevator climbers are staggering. Moving a 1,000-kilogram payload from Earth's surface to geostationary orbit requires roughly 10 billion joules of energy, equivalent to about 2,800 kilowatt-hours of electricity. That's enough to power an average American home for 3 months. And that's just for a relatively small payload. Larger cargo loads or passenger vehicles would require proportionally more energy. But energy isn't the only consideration. The climber also needs power, the rate at which energy is delivered. A climber moving at 200 kilometers per hour would need to maintain an average power consumption of several megawatts throughout its journey. That's comparable to the power output of a small electrical generating station. But it all has to be delivered to a moving vehicle in space. The first option engineers have considered is onboard energy storage. The climber could carry its own power source, using batteries, fuel cells, or even small nuclear reactors. This approach offers maximum independence and reliability, but it comes with severe weight penalties that make it impractical for most applications. Let's do the math on battery power. The best lithium-ion batteries available today store about 250 watt-hours per kilogram. To carry enough batteries for the journey to geostationary orbit, our 1,000-kilogram climber would need over 11,000 kilograms of batteries. The batteries would outweigh the payload by more than 10 to 1, making the system economically unviable. Fuel cells offer better energy density than batteries, but they still require carrying both fuel and oxidizer. Even with hydrogen fuel cells, which have the best energy-to-weight ratio of any chemical system, the fuel mass would still be several times the payload mass. This might be acceptable for specialized missions, but it defeats the purpose of having an efficient transportation system. Nuclear power sources offer much higher energy densities, but they bring their own challenges. Small nuclear reactors or radioisotope thermal generators could potentially power a climber, but the shielding required to protect passengers and cargo from radiation would add enormous weight. Nuclear-powered climbers might work for unmanned cargo missions, but they're unlikely to be accepted for passenger service. Given the limitations of onboard power, most space elevator designs rely on beaming energy to the climber from external sources. This wireless power transmission technology has been demonstrated on a small scale, but scaling it up to space elevator requirements presents significant challenges. Laser power beaming is the most developed approach. High-powered lasers on Earth's surface would beam energy directly to photovoltaic panels on the climber. The laser light carries energy through space at the speed of light, allowing precise targeting and rapid power delivery. This system could potentially provide megawatts of power to climbers anywhere along the cable. The laser system would require multiple ground stations positioned around the world to maintain continuous coverage as Earth rotates. Each station would need laser arrays capable of generating tens of megawatts of power with extremely high beam quality. These aren't ordinary laser pointers. We're talking about industrial-scale laser systems comparable to those used for materials processing or military applications. Atmospheric effects pose major challenges for laser power beaming. Earth's atmosphere absorbs and scatters laser light, reducing the amount of power that reaches the climber. Clouds, fog, rain, and atmospheric turbulence can all disrupt the laser beam. Water vapor is particularly problematic, as it strongly absorbs infrared light at wavelengths commonly used for power beaming. To minimize atmospheric losses, laser power systems would likely use wavelengths around 800 to 1000 nanometers, where atmospheric transmission is relatively good. Even so, atmospheric losses could reduce the delivered power by 20 to 50% under typical conditions, and much more during bad weather. Beam targeting and tracking represent another technical challenge. The laser must accurately track the climber as it moves along the cable, maintaining precise alignment despite atmospheric turbulence and the Earth's rotation. The targeting system must compensate for atmospheric refraction, which bends the laser beam as it passes through air layers of different density. Safety considerations for high-powered laser systems are paramount. A megawatt-class laser beam could instantly blind pilots or passengers in aircraft that accidentally intersect the beam. The laser system would need sophisticated safety interlocks to shut down immediately if any unauthorized object enters the beam path. This requires continuous monitoring of the airspace around each laser facility. Photovoltaic panels on the climber must be highly efficient to convert the laser light back into electricity. Conventional solar panels achieve efficiencies around 20%, but specialized laser power receivers can reach efficiencies over 50% when optimized for specific laser wavelengths. Even so, the climber would need large arrays of these receivers to capture megawatts of power. Heat management becomes critical in laser power systems. Both the ground-based lasers and the climber's photovoltaic receivers generate substantial waste heat that must be dissipated. The lasers need massive cooling systems to prevent overheating, while the climber needs radiators to reject heat in the vacuum of space, where convective cooling is impossible. Microwave power transmission offers an alternative to laser systems. This approach uses large antenna arrays to beam power as focused microwave radiation. Microwave beaming has some advantages over lasers, including better atmospheric penetration and less sensitivity to weather conditions. The most famous demonstration of microwave power beaming was conducted by NASA in the 1970s. Researchers successfully transmitted power from a large transmitting antenna to a receiving antenna located several kilometers away, achieving overall efficiency around 80%. This proved the basic concept, though the scale was much smaller than what a space elevator would require. Microwave power systems would require enormous antenna arrays, potentially kilometers in diameter. The transmitting antenna must be precisely aimed at the climber's receiving antenna throughout the journey. Unlike laser beams, microwave beams naturally diverge over long distances, so maintaining adequate power density at the climber becomes increasingly difficult as the distance increases. The frequency selection for microwave power beaming involves trade-offs between atmospheric absorption, antenna size, and safety considerations. Higher frequencies allow smaller antennas, but suffer more atmospheric absorption. Lower frequencies penetrate the atmosphere better, but require impractically large antennas for good beam focus. Safety concerns for microwave power beaming are different, but equally important as those for laser systems. High-power microwave radiation can cause heating in biological tissues, essentially cooking anything in the beam path. The power levels required for space elevator applications would create exclusion zones around the beam path where no aircraft or spacecraft could safely operate. Hybrid power systems represent a compromise approach that combines multiple power sources. A climber might use onboard batteries or fuel cells for low-power situations, laser power beaming for high-power climb segments, and even regenerative braking to recover energy during descent. This redundancy improves reliability but adds complexity and weight. Power transmission along the cable itself offers another possibility. Electrical conductors integrated into the cable structure could carry power from ground-based sources directly to the climber. This approach eliminates the targeting and atmospheric challenges of wireless power transmission, but it requires the cable to function as both a mechanical support and an electrical transmission line. The cable conductors would need to carry enormous currents, potentially thousands of amperes, to deliver megawatt power levels to climbers at high altitudes. At these current levels, electrical losses in the conductors become significant, requiring superconducting materials or very large conductor cross-sections. The electrical insulation between conductors must also withstand the extreme voltage differences needed for efficient power transmission. Current collection from the cable presents its own challenges. The climber needs a mechanism to make reliable electrical contact with the cable while maintaining smooth mechanical motion. This is similar to the contact systems used by electric trains, but operating in the harsh environment of space with much higher power levels. Lightning protection becomes critical for any electrical system connected to a 100,000 kilometer cable. The cable structure would act as a giant lightning rod, potentially collecting enormous electrical charges during thunderstorms. Surge protection systems would need to handle lightning strikes without damaging the power transmission system or any climbers on the cable. Power management systems on the climber must handle the variable power requirements throughout the journey. During atmospheric ascent, the climber needs power to overcome air resistance and gravity. In the vacuum above the atmosphere, power requirements drop significantly. Near geostationary orbit, the climber might actually generate power through regenerative braking as it slows down. Energy storage on the climber becomes important for managing these power variations and providing backup power during emergencies. Even if the primary power comes from external sources, the climber needs some onboard energy storage to handle temporary power interruptions or emergency situations. The efficiency of the entire power transmission system affects the economics of space elevator operations. Every kilowatt-hour of electricity that doesn't reach the climber represents wasted energy and increased operating costs. System designers must optimize every component, from the power generation source through the transmission medium to the climber's electrical systems. Climbing speed directly affects power requirements and system complexity. Faster climbers need more power to overcome gravity and atmospheric drag, but they also complete their journeys more quickly, reducing the total energy required. There's an optimal speed that minimizes total energy consumption while maintaining reasonable trip times. Current space elevator designs typically assume climbing speeds of 200 to 400 kilometers per hour, resulting in journey times of several days to reach geostationary orbit. These relatively slow speeds are chosen to minimize power requirements and reduce stress on the cable, but they make passenger service less attractive compared to rocket transport. Power system redundancy is essential for safety, especially for passenger-carrying climbers. Multiple independent power sources ensure that a climber can still operate safely if one system fails. Emergency power systems must provide enough energy to safely return the climber to the ground or reach a refuge point where passengers can be rescued. The power infrastructure for a space elevator represents a major engineering undertaking in itself. Ground-based power plants, laser or microwave facilities, and cable-mounted electrical systems would require investments comparable to major national infrastructure projects. However, once built, this power infrastructure could support multiple climbers operating simultaneously, dramatically increasing the throughput of the space elevator system. Despite the challenges, power transmission technology continues advancing rapidly. Improvements in laser efficiency, photovoltaic receivers, and wireless power systems bring space elevator power requirements closer to technical feasibility. The power system may not be the limiting factor for space elevator development, but it represents a critical component that must be perfected for safe and economical operations. The space elevator isn't just an engineering challenge, it's also one of the most expensive infrastructure projects ever conceived. The upfront costs are staggering, potentially reaching hundreds of billions of dollars. But the economic analysis doesn't stop there. The real question is whether this enormous investment could eventually pay for itself by revolutionizing access to space and creating entirely new industries. Let's start with the brutal reality of construction costs. Conservative estimates for building a complete Earth-based space elevator range from $200 billion to $500 billion. To put that in perspective, that's more than the gross domestic product of most countries. It's comparable to building the entire interstate highway system in the United States, except this highway goes to space. The largest single cost component is the cable material itself. Even if carbon nanotube production costs drop dramatically from current levels, the sheer quantity needed is enormous. A space elevator cable would require thousands of tons of ultra-high strength material, with a specific strength far exceeding anything in commercial production today. Current carbon nanotube fiber costs hundreds of thousands of dollars per kilogram for research-grade material. Even with optimistic projections for mass production cost reductions, space elevator-grade material might cost thousands of dollars per kilogram. With a cable mass potentially reaching tens of thousands of tons, material costs alone could exceed $100 billion. But materials are just the beginning. The construction process would require developing entirely new manufacturing capabilities, specialized space vehicles, robotic assembly systems, and ground support infrastructure. The research and development costs for these technologies could easily reach tens of billions of dollars before construction even begins. The Anchor platform represents another major expense. This floating city would need to be larger and more sophisticated than anything ever built for ocean operations. Current estimates suggest the platform alone could cost $20 to $50 billion, including all the facilities needed to support space elevator operations. Launch costs for the initial deployment add another significant expense. Getting the seed cable and construction equipment to geostationary orbit using conventional rockets would require hundreds of launches with total costs potentially exceeding $10 billion. This assumes rocket costs continue their current downward trend driven by reusable launch vehicles. Ground-based infrastructure costs include the laser or microwave power transmission systems, tracking and communication networks, and terrestrial transportation links to the Anchor platform. These supporting systems could easily cost another $20 to $50 billion, depending on the power system design and redundancy requirements. Insurance and risk management costs for such a project would be unprecedented. No insurance company has ever faced the prospect of covering a structure worth hundreds of billions of dollars operating in the hostile environment of space. The insurance premiums alone could add billions to the project costs, assuming coverage is even available. Project management and oversight costs for a decades-long international construction project would also be substantial. The administrative and coordination costs could reach tens of billions of dollars, especially given the need for international cooperation and regulatory compliance across multiple jurisdictions. Despite these enormous upfront costs, the economic case for space elevators rests on their potential to dramatically reduce the ongoing costs of space access. Current rocket launch costs range from roughly $3,000 to $15,000 per kilogram to low Earth orbit, depending on the launch vehicle and mission requirements. Space elevator operating costs could potentially drop space access costs to just a few $100s per kilogram. This represents a cost reduction of 90% or more compared to rocket transportation. Such dramatic cost reductions would fundamentally change the economics of space-based activities. The physics of space elevator operations naturally lead to low marginal costs. Once the elevator is built, the energy cost to lift cargo is simply the electricity needed to power the climbers. At typical industrial electricity rates, the energy cost to lift 1 kilogram to geostationary orbit would be less than $10, a tiny fraction of current rocket costs. Climber vehicles would have operating costs more similar to railroad trains than rockets. They could operate for thousands of trips with routine maintenance, spreading their capital costs across enormous cargo volumes. Unlike rockets, which are largely destroyed with each launch, space elevator climbers would be reusable infrastructure. The capacity advantages of space elevators are equally impressive. A single space elevator could potentially transport hundreds of tons of cargo per day, far exceeding the capacity of any conceivable rocket-based transportation system. This high throughput is essential for amortizing the enormous construction costs over reasonable time periods. Let's examine a realistic economic scenario. Assume a space elevator costs $300 billion to build and can transport 100,000 tons per year to orbit at an operating cost of $200 per kilogram. At a charge rate of $500 per kilogram to customers, the elevator would generate $50 billion in annual revenue while covering operating costs and generating a healthy profit margin. With $50 billion in annual revenue, the space elevator would recover its construction costs in about 6 years, not counting financing costs. Add in reasonable financing costs and debt service, and the payback period might extend to 10 to 15 years. For infrastructure projects of this scale, such payback periods are quite reasonable. But the economic benefits extend far beyond just transportation cost savings. Cheap access to space would enable entirely new industries that are currently economically impossible. Space-based solar power, orbital manufacturing, asteroid mining, and large-scale space habitats all become feasible when transportation costs drop by an order of magnitude. Space-based solar power represents perhaps the largest potential market. Orbital solar power satellites could generate clean electricity around the clock without weather interference, beaming power back to Earth via microwave transmission. The global electricity market is worth trillions of dollars annually, providing enormous potential demand for space elevator services. Orbital manufacturing could exploit the unique environment of space for producing materials impossible to make on Earth. Perfect crystals, ultra-pure metals, and specialized pharmaceuticals could all be manufactured in the microgravity environment of space. The space elevator would make it economical to transport both raw materials and finished products for these industries. Space tourism would become accessible to millions rather than just billionaires. If space elevator transportation costs drop to hundreds of dollars per kilogram, a trip to orbit might cost tens of thousands of dollars per person rather than tens of millions. This would create a mass market for space tourism comparable to international air travel. Asteroid mining could provide access to vast mineral wealth in the solar system. Many asteroids contain more platinum, gold, and rare Earth elements than have ever been mined on Earth. The space elevator would make it economical to transport mining equipment to asteroids and return valuable materials to Earth markets. The construction of large-scale space habitats would become feasible with cheap heavy lift capability. Rotating space stations housing thousands of people could be built and supplied via space elevator. These habitats could serve as stepping stones for human expansion throughout the solar system. Scientific research would benefit enormously from routine access to space. Large space telescopes, gravitational wave detectors, and particle physics experiments could be built and maintained in space at reasonable costs. The scientific discoveries enabled by such facilities could drive technological advances with enormous economic value. National security applications also provide significant economic justification. Space-based defense systems, reconnaissance satellites, and communication networks all become more affordable with space elevator transportation. The military and intelligence value of such capabilities could justify substantial government investment in space elevator development. However, the economic analysis must also consider significant risks and uncertainties. The construction timeline could stretch much longer than planned, increasing costs and delaying revenue generation. Technical problems could require expensive redesigns or rebuilds. Market demand for space transportation might not develop as quickly as projected. Competition from alternative technologies poses another economic risk. Advances in rocket reusability, air-breathing launch vehicles, or other space transportation concepts could reduce the cost advantage of space elevators. If rocket costs drop to $1,000 per kilogram through other means, the economic case for space elevators becomes much weaker. Regulatory and political risks are also significant. International disputes over space elevator operations, changes in environmental regulations, or shifts in government space policy could all affect the project's viability. The decades-long construction timeline makes such risks almost inevitable. Market development represents another challenge. Building industries to use cheap space transportation takes time and additional investment. The space elevator operators might need to subsidize early customers or invest directly in space-based industries to generate sufficient demand for their services. Financing such an enormous project would require unprecedented international cooperation. No single country or company could reasonably fund a space elevator alone. International development banks, sovereign wealth funds, and multinational corporations would all need to participate in financing arrangements. The financing structure would likely involve government participation, given the strategic importance and enormous scale of the project. Public-private partnerships, similar to those used for major infrastructure projects, could spread risks and costs across multiple stakeholders while providing reasonable returns to private investors. Revenue-sharing agreements would be complex, given the international nature of space elevator operations. Different countries and organizations contributing to construction costs would expect proportional access to the elevator's capacity. Negotiating these agreements could be as challenging as the technical construction. Operating economics become more favorable over time as the elevator ages and debt is repaid. Once construction costs are recovered, operating margins would be extremely high, generating enormous cash flows for reinvestment or distribution to stakeholders. These cash flows could fund additional space elevators or other space infrastructure projects. The long-term economic impact of space elevators could be transformational. By making space access routine and affordable, they could catalyze the development of a true space economy worth trillions of dollars annually. The initial investment, enormous as it seems today, might appear modest compared to the economic activity it enables. Multiple space elevators would create even greater economic benefits through redundancy and competition. If construction costs could be reduced through experience and technological improvements, building several space elevators around the world might become economically attractive, further reducing transportation costs and increasing capacity. The economic case for space elevators ultimately depends on humanity's long-term commitment to space development. If we view ourselves as a spacefaring civilization with unlimited growth potential beyond Earth, the investment makes perfect sense. If we see space as an interesting but peripheral activity, the costs appear prohibitive. The space elevator economic analysis forces us to decide what kind of future we want to build. Building a space elevator isn't just an engineering and economic challenge. It's also a political minefield that could reshape international relations and challenge the foundations of space law. A structure that connects Earth to space and provides unprecedented access to orbital assets would inevitably become one of the most strategically important pieces of infrastructure in human history. The nation or organization that controls a space elevator would wield enormous power over humanity's expansion into space. The very location of a space elevator makes it inherently political. The cable must be anchored at the equator, severely limiting the possible locations. The countries with equatorial territory include Ecuador, Colombia, Brazil, Gabon, Republic of the Congo, Democratic Republic of the Congo, Uganda, Kenya, Somalia, Maldives, Indonesia, and Kiribati. Most space elevator proposals avoid land-based anchors entirely, favoring ocean platforms positioned in international waters. Even an ocean-based platform raises complex questions about sovereignty and jurisdiction. International waters are not truly lawless. They're governed by a complex web of international maritime law, primarily the United Nations Convention on the Law of the Sea. However, these laws were written long before anyone contemplated permanent structures extending from the ocean surface to space. The platform would likely be classified as an artificial island under maritime law, giving the nation that builds it certain rights within a limited zone around the structure. But the cable extending into space would pass through the airspace of whatever nation lies directly below the equatorial anchor point. This creates immediate conflicts between the rights of the platform owner and the sovereign rights of the underlying nation. Air traffic control presents the first major jurisdictional challenge. The space elevator cable would create a permanent obstacle to aviation, requiring aircraft to route around its position. The International Civil Aviation Organization would need to establish new regulations for managing air traffic near space elevator structures. Nations downstream of the prevailing winds would need to coordinate their airspace management with elevator operations. The cable itself raises unprecedented questions about territorial sovereignty. Current international law recognizes national sovereignty over airspace up to the boundary of space, typically defined as 100 kilometers altitude. Beyond that point, space is considered the province of all mankind under the Outer Space Treaty of 1967. But no existing law addresses structures that span both domains. Does the nation beneath the cable have sovereign rights over the portion passing through its airspace? Can it regulate climate traffic, impose fees, or even prohibit certain activities? What happens if political relationships change and the underlying nation becomes hostile to the elevator operators? These questions have no clear answers under existing international law. The Outer Space Treaty itself creates significant complications for space elevator development. The treaty prohibits national appropriation of celestial bodies and requires that space activities be conducted for the benefit of all mankind. It also makes nations responsible for their space activities, including those conducted by private entities under their jurisdiction. A space elevator would clearly be a space activity under the treaty, but it's unclear which nation would bear responsibility for its operations. If built by an international consortium with participation from multiple nations, the responsibility becomes even more complex. The treaty's requirement for international cooperation and benefit sharing could complicate commercial operations of the elevator. Military applications of space elevators pose particularly sensitive political challenges. The elevator would provide rapid, cheap access to space for military satellites, weapons systems, and reconnaissance platforms. Any nation controlling a space elevator would have enormous advantages in space-based military activities, potentially destabilizing the global balance of power. The dual-use nature of space elevator technology makes arms control extremely difficult. The same infrastructure used to launch communication satellites could also deploy weapons systems. The same climber vehicles carrying peaceful cargo could transport military equipment. Traditional arms control verification becomes nearly impossible. when civilian and military activities are so intertwined. Space elevators could also be vulnerable to military attack, making them potential targets in any future conflict. The cable represents an enormous stationary target that would be difficult to defend against determined attackers. A successful attack that severed the cable could create debris that threatens other space assets, potentially triggering broader conflicts. The defensive requirements for protecting a space elevator would be substantial. The entire length of the cable, from ground level to the counterweight, would need monitoring and protection. This could require new types of defensive systems, including space-based platforms and directed energy weapons. The militarization required to protect the elevator could itself become a source of international tension. Economic dominance through space elevator control presents another political challenge. The organization controlling the elevator would have enormous influence over who can access space and at what cost. This economic leverage could be used to advance political goals, potentially creating conflicts with nations that depend on space access for their security or economic interests. International cooperation would be essential for space elevator development, but cooperation brings its own political complications. Different nations have varying technical capabilities, financial resources, and political systems. Negotiating agreements that fairly distribute costs, benefits, and control among diverse international partners has historically proven extremely difficult. The International Space Station provides both positive and negative lessons for space elevator cooperation. While the ISS has successfully operated as an international partnership for over 2 decades, it has also faced numerous political challenges, including tensions between the United States and Russia that have affected station operations. A space elevator partnership would be far more complex than the ISS, involving much larger financial commitments and longer time horizons. The partnership would need to survive changes in government, economic crises, and international conflicts over the decades required for construction and operation. History suggests that such long-term international cooperation is challenging to maintain. Technology transfer and intellectual property rights would create additional political tensions. The advanced materials and technologies required for space elevator construction would have significant military and commercial applications beyond the elevator itself. Nations contributing to the project would want to protect their technological advantages while also sharing enough information to enable successful construction. Export control laws in various countries could complicate international cooperation on space elevator technology. Many of the materials and systems involved would likely be classified as dual-use technologies subject to export restrictions. Obtaining the necessary approvals for international technology sharing could take years and might be impossible in some cases. Environmental politics also factor into space elevator development. The construction and operation of such a massive structure would have environmental impacts both on Earth and in space. Environmental groups might oppose the project based on concerns about space debris, electromagnetic radiation from power transmission systems, or impacts on marine ecosystems around the Anchor platform. The space elevator could also become entangled in climate change politics. If positioned as a solution for space-based solar power or other climate mitigation technologies, it might gain political support from environmental advocates. Conversely, if seen as enabling unsustainable expansion of human activities into space, it could face environmental opposition. International law governing space elevators would need to be developed from scratch. The existing framework of space law, based on treaties from the 1960s and 70s, simply doesn't address the unique legal issues raised by permanent Earth to space transportation infrastructure. New international agreements would be necessary to establish clear rules for space elevator operations. These new legal frameworks would need to address questions of liability for accidents, environmental damage, and interference with other space activities. They would need to establish safety standards, operational procedures, and dispute resolution mechanisms. Negotiating such agreements among the world's nations would likely take years or decades. potentially delaying space elevator development. Regulatory oversight of space elevator operations would require new international institutions or major expansions of existing ones. The International Telecommunication Union currently coordinates satellite orbital positions and radio frequencies. A similar organization might be needed to coordinate space elevator operations, climate traffic, and integration with other space activities. National security concerns could override international cooperation in space elevator development. If one nation or bloc appeared to be gaining decisive advantages in space through elevator technology, others might feel compelled to develop competing systems or take measures to prevent their rivals from achieving space dominance. The possibility of space elevator proliferation creates additional political challenges. If the technology proves successful, multiple nations or organizations might want to build their own elevators. Multiple space elevators operating simultaneously would require coordination to prevent conflicts and ensure safety. But competition between elevator operators could undermine such cooperation. Resource allocation and capacity sharing would be politically contentious issues for any international space elevator project. Which countries get priority access during capacity constraints? How are emergency situations handled when multiple nations need urgent space access? What happens when political relationships deteriorate between partner nations? The precedent established by the first space elevator would significantly influence the development of future space transportation infrastructure. The legal, political, and economic frameworks created for the initial project would likely be applied to subsequent elevators, making the initial negotiations critically important for the long-term development of space transportation. Despite these formidable political challenges, the potential benefits of space elevators are so significant that international cooperation might prove possible. The project could serve as a model for peaceful international collaboration on major technological challenges, similar to the international cooperation that has characterized civilian space exploration. Success would require unprecedented levels of international coordination, legal innovation, and political compromise. The nations and organizations willing to undertake such cooperation would need to demonstrate remarkable foresight and commitment to shared goals. Whether humanity can rise to this political challenge may ultimately determine whether space elevators remain forever in the realm of science fiction or become the foundation for humanity's expansion into space. While an Earth-based space elevator pushes the boundaries of materials science and engineering, space elevators on other worlds present dramatically different challenges and opportunities. The reduced gravity and different orbital dynamics of the Moon and Mars make space elevators not only more feasible with current technology, but potentially essential infrastructure for human expansion throughout the solar system. Let's start with the Moon, where the physics work in our favor in remarkable ways. The Moon's surface gravity is only 1/6 that of Earth, immediately reducing the stress on any space elevator cable by a factor of 6. But that's just the beginning of the advantages. The Moon has no atmosphere, eliminating weather, wind loads, and atmospheric drag that complicate Earth-based designs. The Moon's rotation period is 27.3 Earth days, meaning its synchronous orbit, where satellites remain fixed above one point on the surface, is much closer than Earth's geostationary orbit. A lunar synchronous orbit sits at only about 88,400 kilometers from the Moon's center, or about 86,600 kilometers above the surface. That's shorter than an Earth-based space elevator, despite having to reach a more distant relative orbit. But here's where lunar space elevators get really interesting. The Moon is tidally locked to Earth, meaning the same side always faces our planet. This creates a unique opportunity that doesn't exist anywhere else in the solar system. A space elevator cable extending from the Earth-facing side of the Moon wouldn't stop at lunar synchronous orbit. It could continue much farther out, all the way to one of the gravitational balance points between Earth and the Moon. The Earth-Moon Lagrange point L1 sits about 61,500 kilometers above the lunar surface on the Earth-facing side. At this point, the gravitational pull of Earth exactly balances the gravitational pull of the Moon, plus the centrifugal force from orbital motion. A space elevator cable extending from the Moon's surface to L1 would experience tension throughout its length, just like an Earth-based elevator. But we can do even better than that. The cable could extend all the way to Lagrange point L2, which sits about 65,200 kilometers beyond the far side of the Moon. An elevator cable reaching L2 would provide access to deep space trajectories toward Mars, the asteroids, and the outer solar system. Spacecraft could literally ride the elevator away from Earth and Moon gravity, getting a free boost toward their destinations. The material requirements for a lunar space elevator are dramatically more modest than for Earth. The reduced gravity and lack of atmosphere mean that existing materials like Kevlar or Xylon could potentially work for lunar elevator construction. We wouldn't need to wait for perfect carbon nanotube production technology. A lunar space elevator could be built with materials we can manufacture today. The reduced material requirements also mean much lower costs. Instead of requiring thousands of tons of exotic carbon nanotube fiber costing hundreds of billions of dollars, a lunar elevator might need only hundreds of tons of high-strength polymer fiber costing millions or low billions of dollars. The cost difference between lunar and Earth elevators could be 2 orders of magnitude. Construction of a lunar elevator would also be much simpler than an Earth-based system. Without weather, atmosphere, or strong gravity to complicate operations, robotic systems could assemble the cable with far less risk and complexity. The construction timeline could be years instead of decades, and the technical risks would be much more manageable. A lunar space elevator would transform the economics of lunar operations and deep space exploration. Currently, landing on the Moon requires sophisticated rocket systems capable of powered descent through vacuum. Taking off from the Moon requires another rocket stage with enough fuel to reach lunar escape velocity. These requirements make lunar missions extremely expensive and limit the massive equipment and supplies that can be transported. With a lunar space elevator, landing would become as simple as docking with the bottom of the elevator cable and riding down to the surface. No fuel would be needed for the descent. Taking off would be equally simple. Just ride the elevator up to whatever altitude provides the desired orbital velocity or escape trajectory. The elevator would make lunar mining operations economically viable. Rare Earth elements, helium-3 for fusion reactors, and other valuable materials could be extracted from the Moon and transported to Earth or space habitats at reasonable costs. The Moon could become a major source of raw materials for space-based industries. Mars presents another compelling case for space elevator technology. Mars has about 38% of Earth's surface gravity, making space elevators much more feasible than on Earth, but more challenging than on the Moon. Mars also has a thin atmosphere that creates some weather effects, though much less severe than Earth's dense atmosphere. The key advantage for Mars elevators is the planet's rapid rotation. Mars rotates once every 24 hours and 37 minutes, very similar to Earth. However, Mars' synchronous orbit sits at only about 20,300 kilometers above the surface, compared to 35,800 kilometers for Earth. This shorter distance significantly reduces the cable length and material requirements. A Martian space elevator cable would need to extend to about 53,000 kilometers from the planet's center to provide adequate counterweight. That's about half the length of an Earth-based elevator, dramatically reducing the total mass of cable material required. The reduced gravity and shorter cable length mean that materials significantly weaker than perfect carbon nanotubes could work for Mars elevator construction. The thin Martian atmosphere, while creating some complications, also provides advantages. the atmosphere is thick enough to allow aerobraking for spacecraft arriving from Earth, but thin enough that atmospheric drag on the elevator cable would be minimal. Dust storms on Mars could pose challenges for elevator operations, but they're predictable seasonal phenomena that could be planned around. Mars elevators would be essential infrastructure for human colonization of the red planet. Moving people and supplies from Mars' orbit to the surface currently requires complex entry, descent, and landing systems. The elevator would make this process routine and safe. More importantly, it would make return trips to Earth economically feasible, allowing true two-way transportation between the planets. The elevator could also support terraforming efforts by providing cheap access to orbital infrastructure. Solar power satellites, atmospheric processing equipment, and magnetic field generators could all be deployed and maintained via the elevator. Large-scale engineering projects that could transform Mars into a more Earth-like world would become practical with elevator transportation. Phobos, one of Mars's 2 small moons, could play a role in Martian space elevator systems. Phobos orbits very close to Mars at an altitude of only about 6,000 kilometers. While this orbit is inside the synchronous altitude, Phobos could serve as a source of counterweight material for elevator construction, or as a staging area for elevator operations. The different gravitational environments of the Moon and Mars also create opportunities for specialized elevator designs. Lunar elevators could use very lightweight designs optimized for minimal material usage. Martian elevators could incorporate redundancy and safety features more easily due to the relaxed material requirements compared to Earth. Multiple space elevators on different worlds could work together as an integrated transportation network. A lunar elevator could serve as a staging point for missions to Mars, reducing the energy requirements for interplanetary travel. A Martian elevator could support exploration of the outer solar system, providing a launching point for missions to the asteroid belt and beyond. The construction sequence for off-world elevators could begin with the Moon, where technical risks are lowest and existing materials could work. Success with a lunar elevator would provide experience and confidence for tackling the more challenging Martian system. Eventually, Earth-based elevators could complete the network, providing cheap access from our home planet to the entire solar system. Robotic construction would be essential for off-world elevators. Unlike Earth-based systems that might use human construction crews, lunar and Martian elevators would likely be built entirely by robots. The reduced complexity of construction in low-gravity, vacuum environments actually makes robotic assembly more feasible than human construction. Timing of off-world elevator construction could be coordinated with human settlement efforts. Lunar elevators could be built in advance of permanent lunar bases, providing the infrastructure needed to support large-scale human presence. Martian elevators could be constructed during the early phases of Mars colonization, dramatically improving the logistics of expanding human settlements. Power systems for off-world elevators would face different challenges than Earth-based systems. Solar power is more difficult on Mars due to the greater distance from the Sun and frequent dust storms that can block sunlight. However, the reduced power requirements of shorter, lighter elevators make these challenges more manageable. The success of off-world space elevators could provide crucial technology development and operational experience for eventual Earth-based systems. Materials testing, construction techniques, and operational procedures developed for lunar and Martian elevators would inform the design of Earth elevators. Off-world elevators could serve as stepping stones to the ultimate goal of cheap, routine access to space from Earth. International cooperation might be easier for off-world elevators than for Earth-based systems. Since no nation currently has territorial claims on the Moon or Mars, elevator construction could proceed as international projects from the beginning. This could establish cooperative frameworks that could later be applied to Earth-based elevators. The economic case for off-world elevators becomes compelling when viewed as part of a larger space development strategy. While the immediate markets for lunar or Martian elevator services might be limited, these systems could catalyze the development of space-based industries that would eventually justify their costs many times over. Environmental considerations for off-world elevators are much simpler than for Earth-based systems. There are no ecosystems to protect on the Moon or Mars, eliminating many environmental objections. The main environmental concern would be planetary protection protocols to prevent contamination of scientifically interesting areas. Off-world space elevators represent the most practical, near-term path to developing space elevator technology. The reduced technical requirements, lower costs, and simpler political environments make them much more achievable than Earth-based systems. Success with off-world elevators could pave the way for the ultimate prize, a space elevator connecting Earth to the cosmos and opening the space frontier to all humanity. As we stand at the threshold of the 21st century's greatest engineering challenge, the path to building space elevators is becoming clearer, even as it remains daunting. The technology roadmap stretches decades into the future, requiring breakthrough advances in materials science, unprecedented international cooperation, and sustained commitment across multiple generations. Yet, for the first time in human history, we can see a realistic pathway from today's technology to a working space elevator. The immediate future of space elevator development lies not in building the final system, but in developing and testing the component technologies that will make it possible. Materials science research continues to push the boundaries of what's achievable with carbon nanotubes, graphene, and other exotic materials. Every advance in nanotube production, every improvement in fiber strength and length, brings us closer to the materials threshold needed for space elevator construction. Current research focuses on solving the fundamental challenges of nanotube manufacturing. Scientists are developing new techniques for growing longer individual nanotubes, improving the alignment of tubes in composite fibers, and reducing defects that weaken the final product. Some researchers are exploring biological approaches, using modified bacteria or other organisms to produce nanotube precursors with better properties than purely synthetic methods. The timeline for achieving space elevator grade materials remains uncertain, but progress is accelerating. Laboratory demonstrations have already achieved the required strength levels over short distances. The challenge now is scaling these successes to the kilometers and eventually tens of thousands of kilometers needed for practical space elevator cables. Conservative estimates suggest this could happen within 20 to 30 years, while optimistic projections put it closer to 10 to 15 years. Parallel development of related technologies is equally important. Space tethers, much shorter than full space elevators but using similar principles, are already being tested in space. These systems demonstrate the fundamental physics of tethered structures in orbit, while providing practical experience with the challenges of operating long cables in the space environment. The European Space Agency has conducted several tether experiments, including the Young Engineers Satellite 2 mission that successfully deployed a 36-kilometer tether in space. While far shorter than a space elevator, these missions prove that very long structures can be deployed and operated in orbit. Each mission provides valuable data on tether dynamics, space environment effects, and operational procedures. Skyhooks represent an intermediate step toward full space elevators. These are rotating tethered structures in orbit that can catch payloads from suborbital trajectories and boost them to higher velocities. While still requiring advanced materials, skyhooks are much shorter than space elevators and could be built with materials closer to current capabilities. A successful skyhook demonstration could provide crucial experience for eventual space elevator construction. Orbital rings represent another alternative approach to space-based transportation infrastructure. Instead of a single cable extending from Earth to space, orbital rings would encircle the entire planet at orbital altitude, supported by magnetic levitation or other non-mechanical means. While even more challenging to build than space elevators, orbital rings could provide multiple access points to space and might be more resilient to damage. The development pathway likely involves a progression from simpler to more complex systems. Short space tethers could evolve into longer ones, eventually reaching the scale needed for momentum exchange or partial orbital assist. Suborbital skyhooks could demonstrate rotating tether technology before full orbital systems are attempted. Each step builds capabilities and confidence for the next level of complexity. Robotic construction technology is advancing rapidly and will be essential for space elevator development. Current robotic systems can perform increasingly sophisticated assembly tasks in space. The James Webb Space Telescope demonstrated complex robotic deployment of large structures in space, while satellite servicing missions have shown robots can perform delicate operations on orbital infrastructure. Artificial intelligence and machine learning are revolutionizing robotic capabilities. Future construction robots for space elevators will need to operate autonomously for extended periods, making complex decisions about assembly procedures and responding to unexpected situations. The combination of advanced AI with improved robotic hardware could make the robotic construction of space elevators feasible within the next few decades. Power transmission technology for space elevators is also advancing on multiple fronts. Laser power beaming demonstrations are achieving higher efficiencies and longer ranges. Microwave power transmission research continues to improve beam focusing and receiver efficiency. Wireless power technology, developed for terrestrial applications, provides lessons applicable to space elevator power systems. The commercial space industry is creating an ecosystem that supports space elevator development. Reusable rockets are dramatically reducing launch costs, making it more affordable to deploy space elevator components. Private space companies are developing experience with large-scale space operations that would be essential for elevator construction and operation. Space manufacturing capabilities are beginning to emerge, with companies planning to produce fiber optics, pharmaceuticals, and other products in orbit. These early space industries could provide both markets for space elevator services and experience with the types of operations that elevators would enable on a much larger scale. International cooperation frameworks are slowly developing through existing space projects. The International Space Station has demonstrated that complex space infrastructure can be built and operated through international partnerships. The Artemis Accords represent a new model for international cooperation in space exploration. These frameworks could evolve to support space elevator development. NASA continues to fund space elevator research through its innovative Advanced Concepts program. The agency has supported studies of space elevator materials, power systems, and operational concepts. While NASA hasn't committed to building a space elevator, the agency recognizes its potential importance and continues to advance the underlying technologies. The Japan Aerospace Exploration Agency has been even more explicit about space elevator goals. JAXA has funded research into space elevator technologies and has stated ambitious timelines for development. Japanese companies like Obayashi Corporation have announced plans to build space elevators by 2050. Though these timelines are widely considered optimistic by technical experts. Private companies are also investing in space elevator research. While no company has yet committed to building a full space elevator, several are developing related technologies that could contribute to eventual elevator construction. Companies working on carbon nanotube production, space tethers, and robotic systems all contribute to the technology base needed for space elevators. The business case for space elevators continues to strengthen as space commerce grows. The global space economy is now worth over $400 billion annually and growing rapidly. Launch costs, while decreasing, still represent a major barrier to many space applications. The dramatic cost reductions possible with space elevators would unlock entirely new markets and applications. Space tourism is emerging as a significant market that could justify space elevator investment. While current space tourism serves only the ultra-wealthy, space elevators could make space travel accessible to millions of people. The tourism market for space elevators could potentially reach tens of billions of dollars annually. Asteroid mining represents an even larger potential market. There are asteroids in the solar system containing more precious metals than have ever been mined on Earth. Space elevators would make it economically feasible to transport mining equipment to asteroids and return valuable materials to Earth. The potential value of asteroid resources runs into the trillions of dollars. Climate change considerations add urgency to space elevator development. Space-based solar power could provide clean energy to Earth on a massive scale, but only if transportation costs to space drop dramatically. Space elevators could enable solar power satellites that dwarf terrestrial renewable energy installations, providing a pathway to carbon-neutral energy systems. The development timeline for space elevators remains highly uncertain. Conservative estimates suggest the first space elevator could be operational by 2070 to 2100, assuming steady progress in materials, science, and international cooperation. Optimistic projections put the timeline closer to 2040 to 2060, assuming breakthrough advances in nanotube production and accelerated development programs. Lunar space elevators could come much sooner, potentially within 20 to 30 years. The reduced technical requirements for lunar systems make them achievable with nearer-term technology advances. A successful lunar elevator could provide crucial experience and confidence for Earth-based systems. The most likely development path involves multiple phases of technology demonstration and capability building. Phase 1 might focus on achieving the materials breakthrough needed for space elevator construction. Phase 2 could involve building and testing suborbital or short orbital tethers. Phase 3 might include construction of a lunar space elevator. Phase 4 would culminate in an Earth-based space elevator. Each phase would build capabilities and reduce risks for subsequent phases. The timeline could span 30 to 50 years from start to finish, requiring sustained commitment across multiple governments and organizations. However, the benefits of success would justify even such an extended development program. Technical risks remain significant throughout the development process. Materials science breakthroughs cannot be guaranteed on any particular timeline. Construction challenges in space could prove more difficult than anticipated. Operational hazards, like space debris, could make space elevators impractical despite technical success in construction. Political and economic risks are equally important. International cooperation required for space elevator development could break down due to geopolitical tensions. Economic priorities could shift, reducing support for long-term infrastructure projects. Public opinion could turn against space development if other priorities become more pressing. Despite these risks, the fundamental drivers for space elevator development continue to strengthen. Growing space commerce, climate change pressures, resource depletion on Earth, and human expansion into space all point toward the need for better space transportation. Space elevators represent the most promising solution to the transportation bottleneck that currently limits space development. The next decade will be crucial for space elevator development. Materials science research will determine whether the required breakthrough in nanotube technology occurs. International space cooperation frameworks will evolve in ways that either support or hinder major space infrastructure projects. Commercial space markets will either grow large enough to justify space elevator investment or remain niche applications. Success in space elevator development would mark a turning point in human history. For the first time, space would become truly accessible to ordinary people and organizations. The solar system would open to human expansion and resource utilization. Earth would no longer be humanity's only home, but rather the first stop in our expansion throughout the cosmos. The road ahead is long and uncertain, but the destination is clear. Space elevators represent humanity's best hope for becoming a truly spacefaring civilization. Whether we have the vision, persistence, and cooperation needed to build them will determine whether the 21st century becomes the era when humanity first reached for the stars, or merely the century when we dreamed of doing so. The choice and the challenge lies ahead of us. The space elevator could be the most transformative infrastructure project in human history, a literal bridge between Earth and space that would fundamentally change our relationship with the cosmos. We have journeyed through the physics that make it possible, the engineering challenges that make it difficult, and the human factors that will ultimately determine whether it becomes reality. The physics is sound, the mathematics work beautifully. Objects at geostationary orbit naturally want to stay there, balanced between gravity pulling inward and centrifugal force pulling outward. A cable extending from Earth's surface beyond geostationary orbit would remain under tension, creating a permanent pathway to space. This isn't science fiction, it's orbital mechanics, as well understood as the laws that keep satellites in their orbits and planets around the sun. The engineering is imaginable. While building a structure 100,000 kilometers long presents unprecedented challenges, each individual component represents an extension of existing technology rather than something completely new. We know how to build strong materials. We know how to construct in space. We know how to manage complex projects. The space elevator requires us to do all of these things better than ever before, but not to invent entirely new categories of technology. The economics make sense. Yes, the upfront costs would be enormous, potentially hundreds of billions of dollars. But the operational advantages would be equally enormous. Reducing space transportation costs by 90% or more would unlock trillion-dollar markets in space tourism, orbital manufacturing, asteroid mining, and space-based solar power. The investment would pay for itself many times over, yet one critical piece remains missing. We still don't have materials strong enough to build the cable. Carbon nanotubes show incredible promise in laboratory tests, achieving strengths far beyond what space elevators require. But scaling from laboratory samples to 100,000 kilometer cables remains an unsolved challenge. Every gram of space elevator cable must be perfect, with no weak points that could trigger catastrophic failure. This materials challenge is not a fundamental barrier. It's an engineering problem waiting for a solution. Research laboratories around the world are making steady progress in nanotube production, improving both strength and length with each advance. The question is not whether we will develop space elevator-grade materials, but when. When that breakthrough comes, and it could happen within our lifetimes, humanity will face a choice. Do we commit the resources and international cooperation needed to build this ultimate infrastructure project? Do we have the vision to invest decades and hundreds of billions of dollars in something that would benefit not just our generation, but all generations that follow? The space elevator represents more than just a transportation system. It embodies humanity's greatest aspirations for our future among the stars. For thousands of years, humans have looked up at the night sky and wondered what lies beyond our world. For decades, we have sent brave astronauts and sophisticated robots to explore space, but always at enormous cost and risk. The space elevator would make space accessible to everyone, not just trained astronauts or billionaire tourists, but ordinary people pursuing ordinary dreams in an extraordinary environment. Students could study astronomy from orbital classrooms. Artists could create in the microgravity environment of space. Families could vacation among the stars. More than that, the space elevator would enable us to build a true space-based civilization. Massive space habitats housing millions of people could be constructed with materials easily transported up the elevator. Solar power satellites could provide clean energy for Earth, while space-based industries create products impossible to manufacture under gravity. The resources of the entire solar system would become accessible. Asteroids containing more platinum than exists in all of Earth's crust could be mined and transported to orbital facilities. The Moon could become a source of helium-3 for fusion reactors or rare earth elements for advanced electronics. Mars could be terraformed using equipment and supplies lifted from Earth via space elevator. But perhaps most importantly, the space elevator would give humanity a backup plan. As long as all of human civilization remains confined to Earth, we remain vulnerable to catastrophic events that could end our species. Asteroid impacts, supervolcanic eruptions, nuclear wars, or climate change could threaten our survival. A space-based civilization, supported by space elevator infrastructure, would ensure that human knowledge, culture, and consciousness survive no matter what happens to our home planet. The challenges are real and significant. Building the space elevator would require unprecedented international cooperation at a time when global politics seems increasingly fragmented. It would require sustained commitment across multiple decades at a time when political attention spans seem to be shrinking. It would require public support for spending enormous sums on a project whose benefits might not be fully realized for generations. Yet humanity has accomplished seemingly impossible things before. We built transcontinental railroads across mountain ranges and deserts. We connected continents with underwater cables for communication. We sent humans to the Moon and built the International Space Station through cooperation between former enemies. We created the Internet, decoded the human genome, and developed vaccines for global pandemics in record time. Each of these achievements required vision, persistence, and the willingness to invest in a future that the builders might not live to see. The space elevator demands the same qualities, but on a scale larger than anything we have attempted before. The choice before us is ultimately about what kind of species we want to be. Do we want to remain forever bound to the surface of one small planet, or do we want to become a spacefaring civilization capable of thriving throughout the solar system? Do we want our great-grandchildren to still be struggling with the limitations of rocket transportation, or do we want to give them routine access to the infinite frontier of space? The space elevator is not inevitable. It will only be built if enough people believe in its importance and commit to making it happen. That means supporting the research needed to develop space elevator materials. It means advocating for international cooperation on space infrastructure projects. It means accepting that some of humanity's greatest achievements require investments whose payoffs extend far beyond a single human lifetime. The elevator cars of the future might carry your descendants on their journey to the stars. The first space elevator passenger could be alive today, perhaps watching this video, perhaps inspired by these words to pursue a career in the technologies that will make it possible. The path to the stars might start with a simple elevator ride, a gentle acceleration upward from Earth's surface, through the blue sky and into the black of space, carrying the hopes and dreams of humanity toward our destiny among the cosmos. The question is not whether such a future is possible. The question is whether we have the courage and commitment to build it. The space elevator could be humanity's greatest achievement, our first permanent bridge to the infinite. When we find the materials strong enough to hold the dream together, the path to the stars will be open. Until then, we reach upward with our science, our engineering, and our imagination, climbing toward that distant day when the elevator doors open and the universe welcomes us home.